Hello and welcome to lecture number 3 in the course Advanced Robotics Applications. In the last two lectures, I discussed about automation, robotics, where robotics came from, the historical aspects of robotics. Then we talked about, very briefly, we talked about intelligence. When we say AI, what do we mean? When we say a robot is intelligent robot, what do we mean and what are the ways of checking it? And then we talked about joints. That is, you can have different kind of joints like prismatic joints, revolute joints, cylindrical joints, and then ball and socket joint. And by using different kind of joints, we can make different kind of robots. And the structure of the robot would be different, and hence the work volume or the shape of the work volume also would be different. Today we'll move on to transformations. That is, when a robot moves in space, how do you relate the position and orientation of the end effector with respect to the base of the robot? Okay, so let's start the lecture for today on transformations. Now let me explain what I was just trying to explain, is that we have a robot. Let's say the robot is fixed, the base is fixed, and is connected by joints, and this is the end effector of the robot or the gripper of the robot. Now, how does the controller work? Basically, at every joint we'll be having a motor. The motor will be powered by a voltage source. There'll be an encoder at the back, and there'll be a gear in front. Okay, so the motor will rotate, the joints will, because of which the joints will rotate, and when the joint rotates, the end effector is going to move. So that's how the controller actually works. So if you want to go from some point to some point, let me say the manipulator is here, and I want the links to go there. Just for example, I want the manipulator to do like this. So it essentially means that this link has to move by this much angle. The second link also will have to move, and the third link will move by some angle. Okay, so theta 1, theta 2, theta 3 will all move by some angles. So the controller has to move the links by the corresponding angle so that the end effector comes from this point and reaches that point in some time, let's say time t. Okay, so the controller needs to know by how much each joint has to move, by how much angle each joint has to move. And that we can get from the inverse kinematics. As we go along, we'll talk about forward kinematics and inverse kinematics, which gives the relation between the end effector position orientation with respect to the joint angles. So this means that this basically means that we need to know how much every joint has to move to take the end effector from some point to some other point. Okay. Now, how do I know the position and orientation of the end effector with respect to the base frame? We assign access to to each of the joints. So let me draw it again here. So this is my robot. Okay, let me say the robot is here again. So I need to know the position orientation of the gripper with respect to the base frame. Now, I fix the base frame as the fixed frame. So let me fix this as a fixed frame. So I assign axis. So I will explain what is an axis as we go along. So we are going to define axis to each of the joints. So I say Z0 and Z1 is here, X0 is here, X1 is in this direction, Z2 is here, Z3 is here, and Z4 is there. So this is my X2, this is my X3, and that's my X4. Okay, so I need to know the relation between the position orientation, which is the of the end effector, which is defined by the frame 4. So if I want to know the relation between the fourth frame and the zero frame, then I need to go from the fourth frame to the third frame, then third frame to second frame to first frame, and then first frame to zero frame. Okay, so I move from one frame to the previous frame like that. Okay, now if you look at the relation between the fourth frame and the zero frame. Okay, now let me look at the relation between the fourth and the zero frame. So what we see here is that the fourth frame has an X4 which is in that direction, X0 is in this direction. So there's an angle between the axes. So the first thing that we see is that there is an angle between the axes. Okay, so there is an angle between the axis between 4 and 0 frame. Okay, so this angle exists between frame 4 and frame 0, and this is what we call by a rotation. So frame 4 is rotated with respect to frame 0. Okay, so there is a rotation involved. Okay, so let me call it a rotation. So there is a rotation involved between axis 4 and axis 0. Now the second is the origin of frame 0 is here, and the origin of frame 4 is there. So there is a transformation also, there is a translation involved also. Okay, so there is a rotation and a translation. Okay, so there is a translation between the 0 frame and 4th frame. Okay, so there are two transformations involved. One is a rotation, that's what we see, and the second is a translation. So between any two frames in three-dimensional space, we have a rotation involved and a translation involved. Now, if the frames are the same frame, of course, your rotation will be 0 and your translation will be 0. Okay, so there may be a rotation and transformation, or there may be a rotation or translation. Okay, now, so we'll have to look at first is the rotation transformation, then we'll look at the translation transformation between two frames in space. And I hope you understand why we need to do this, because I need to move from one frame to the next frame in that order to find the relation between the last frame and the 0 frame. Okay. Now I define the word axis. Now what does an axis mean? Okay. Now these are some terms which we very commonly use right from our school days without worrying too much about them. So what is an axis? An axis is a direction in space. Okay, so an axis is a direction in space. Okay, and hence we can say we can have x-axis, y-axis, z-axis, or we can even have more number of axes. Now we said in space. What space? So the space we are talking about is three-dimensional Euclidean space. And this three-dimensional Euclidean space, it is 3D, meaning 3-dimensional, and hence you have 3x, y, and z. There are 3 axes. So it answers two questions: what is an axis, and why there are 3 axes, x, y, z, because we are talking in terms of three-dimensional Euclidean space. Okay. Now we should remember this, because a lot of the properties of the matrices that we are going to deal with will depend on the space we are talking about and the axis system. Now the other thing we can talk about in terms of the 3 axes is that they are orthogonal axis. That means there is 90 degrees between the axes. Okay, so axis is a direction in space. There are 3 axes, x, y, z, and these are orthogonal axes. So x, y, z are orthogonal axes. Okay, so please remember this definitions of an axis and the properties that this axis system has. Okay, now the first transformation we are going to talk about is the rotation transformation. Rotation transformation. Okay, this is defined by r theta. Let's call this z theta. I'll just explain what that means. Now we say that we have a fixed frame. This is a fixed frame. Okay, this is let's say this is the z-axis, this is the x-axis, that's the y-axis as per right-hand rule. Okay, now this is frame A. Now there is another frame. Let's call it frame B. Now frame B is rotated. This is my frame B. This is xB. That's YB, and this is ZB. ZB is the same. Okay, this is Z of B. Now this frame has been rotated by an angle theta about the z-axis. Okay, this is rotated by an angle theta about the z-axis. Okay, you can rotate about x, y, or z. In this case, I'm rotating about z. Okay. Now suppose there is a point P here. So this is a point P, and let me call this P. Now in robotics, we have different frames which are moving, so you always have to define about which frame are you talking about. So this is a frame, this point P is with reference to frame A. Okay, so this has coordinates. Let me say it has coordinates u, v, and w. Okay, now the same point P also has coordinates with respect to frame, this is with respect to frame B, and this is with respect to frame A. PA is equal to xyz. Please note that. Okay, now what does pxyz means? The projection on the x-axis. This is my x, that is my y. Okay, and the projection on the z-axis is z. That you understand. What is the meaning of UVW? UVW means projection on the B frame. Okay, so this is my U. Okay, and correspondingly when I project it here, this is my V. Okay, now let's do a very small construction, and this very small construction is shown here. Let me draw the line here and bring it down here. Now this angle is also theta. Okay, this angle is also theta. Okay, this angle is theta, so this is also theta. Now we want to geometrically find the relation between xyz and UVW. Okay, UVW is the coordinate of the point in the rotated system. So this is in the rotated frame. Okay, so I want to find what is xyz in terms of UVW. Why do I need to do that? If I give you the coordinate in a rotated frame, you can find the coordinate in the reference frame then. Okay, so let me write x is equal to, so what is x equal to? X is this distance is equal to, geometrically if you look at this, what is this distance equal to? Is equal to the full distance minus this distance. Okay, so x is this small distance here, right? So x is equal to this distance, which is equal to u cos theta. Okay, so this full distance, so x is equal to u cos theta minus this distance. What is that distance? This distance is equal to this distance. Now what is this equal to? This is my v. If this is if that is v, if this is v, okay, then if this is v, then that's also v, right? So what we get is u cos theta minus, how much is this equal to? V sin theta. Okay, so this is equal to my v sin theta. So this is v sin theta, so this is v sin theta. So u cos theta minus v sin theta. Okay, what is y equal to? Y is equal to, what is y? Y is this distance, this full distance is y, this full distance is y, which is equal to this much plus that much. Okay, so how much is this much? This much is equal to this much, is equal to u sin theta plus this much. This much is equal to this much, which is equal to v cos theta, right? So we have two x and y, and what about z? Z is equal to w. Okay, so now I can write this in matrix form. Please derive this geometrically. Okay, once you derive it geometrically, you'll be able to understand this very, very clearly. What is the relation between x, y, z and u, v, w? So if I write it in matrix form, this is x, y, and z. This is equal to, this is u, this is equal to cos theta minus sin theta. This is sin theta cos theta 0, 0, 1, 0, 0. This is u, v, w. Okay, now this matrix here is called the rotation matrix and is defined as the rotation about z axis by an angle theta. Okay, this is the way it is written. So this is a first of all, it is a 3 by 3 matrix, and it has some very interesting properties. Now let me just explain the matrix again. So this matrix R z theta is cos theta minus sin theta cos theta 0, 0, 1, 0, 0. This is my matrix. Now it has some very interesting properties. Each of the columns, if this is my x and that's my y and that's my z, then each of the columns mod of x is equal to mod of y is equal to mod of z is equal to 1. So what we see is that each of the columns is equal to 1. Okay, and now why is it equal to 1? Because we defined our axis as unit vectors, and hence mod of each of these columns is equal to 1. Now this matrix is also called a proper orthonormal matrix. Okay, this matrix is also called a proper orthonormal matrix, and a property of that is the inverse of this matrix, inverse of this is equal to the transpose. Okay, another property that it has is determinant of R is equal to 1. Okay, so these are important properties which this matrix has. Determinant is equal to 1, inverse is equal to its transpose, and mod of each of the columns is equal to 1. Okay, now let's look at a very simple example which will clarify what we are trying to explain here. So this matrix, I hope you understood how I derived these three equations, and from this I got the matrix. Please do it by yourself once so that you understand. The construction is very, very simple. Okay, let's have a very simple problem which gives us a deeper understanding of this matrix. So let me say this is a problem. Let's say this is a problem. So a frame B is rotated by 30 degrees about the z-axis of frame A, of let me say fixed frame A, of fixed frame A. So the frame A is of fixed So frame B is rotated by 30 degrees about the z-axis. So these are points to note, 30 degrees and z-axis. So rotation is by 30 degrees about z-axis of fixed frame A. Okay. Now if the coordinate of a point in frame B is given by, let's call this PB is equal to 1, 1, 1, just coordinate 1, 1, 1. What is its coordinate in frame A? Okay, so I hope you understand the question. There is a frame which has been rotated by, so let me say this is my fixed frame. This is my fixed frame A, that's my z-axis, x-axis, y-axis, and there is a frame which is rotated by, this is the rotated frame, this is the rotated frame, this is my x-axis and y-axis of the rotated frame. Now there is a point and the rotation is about the z-axis by an angle 30. So theta is equal to 30 degrees here. So there is a point, here which has a coordinate in frame B which is equal to 1, 1, 1. Okay, now what is the coordinate in frame? So what is this AP? Okay, so it has a coordinate on frame B which is equal to 1, 1 and 1. What is that coordinate in frame A? Okay. So our equation, so two things to note, it is rotation of 30 degrees about the z-axis. So my equation is AP is equal to the rotation matrix Z by an angle 30, okay, into BP. So what is AP, X, Y and Z? This is equal to, the rotation matrix is cos 30. So if you have forgotten, you can just have a look at the previous one. So what we had got is, this is the rotation matrix about the z-axis. So this is the rotation about z-axis, right? Rotation about z-axis. So cos minus sine, sine cos 0, 0, 1. Now, so let me write it, cos 30 minus sine 30. Sine 30. Cos 30, 0, 0, 1, 0, 0. And what is BP? BP has been given by 1, 1, 1. Okay, so now you can put in the coordinates x, y, z is equal to cos 30 minus sine 30. You can find the values, multiply them out, and what we get is 0.366, 1.366 and 1. Okay, so this is the coordinate in the frame A. So that's in frame A. So this rotation matrix relates the coordinates of a point expressed in a rotated system to that of the reference system. So if there is any rotation between frames, you can always come back to the reference frame. Okay, so if the coordinate is given in the rotated frame, you can come back to the reference frame. Okay, now we also said that this rotation matrix has a couple of interesting properties. This is an interesting property, the inverse is the transpose. Okay, that is one. And the other, if you note this matrix very carefully, we rotated about the z-axis. Let me go back here. I rotated about the z-axis, and hence this is a rotation about z. This is 0, 0, this is 0, 0. So there is no change in the z-axis because this is a rotation about z-axis now. So when you're rotating about z-axis, this will remain as 1, indicating that there is no change about the z-axis now. Okay, so these are important properties to note. And the property that the inverse is equal to the transpose. So if I have almost a similar problem here, so let me reverse this problem and say that this is a problem number 2. So a frame B is rotated. Frame B is rotated by, let's say, 30 degrees about exactly the same problem about z-axis of frame A. Okay, now if the coordinate of a point, if the coordinate of a point in frame A, let me reverse it now, is equal to 1, 1, 1. What is the coordinate in frame B? What is PP? Okay, I hope you understand. So we have one frame which is frame A, and there is another frame B. So this is my z-axis, x-axis, y-axis, and there is another frame which is my frame B. So this is my frame B, this x-axis, that's y-axis here. Now there is a point here, the point P. Let me talk about the point P. But PA is given now as 1, 1, 1. The point PA has been given as having coordinate 1, 1, 1. Can you find what is the coordinate of P with respect to frame B? Okay. So in the previous question, we were given the coordinate of the point PP. We were asked to find what is AP. Now I'm giving you the point AP and asking you to find the point BP. Okay, how would you do that? Equation is exactly the same. AP is equal to RZ theta into BP. Okay, now we are given AP and you are given this and you're asked to find that. How would you do that? So BP is equal to RZ theta inverse into AP. That's simple. Now we know what is the transpose of the rotation matrix. The inverse of the rotation matrix is the transpose. So BP will become equal to cos 30 sin 30 minus sin 30 cos 30 0 0 1, and this is 1 1 1. Okay, so BP, how did we get this one? This is the transpose. So what we get here is well, let me write it down here. So R transpose, R inverse is equal to R transpose. So I took the transpose of that matrix and this is what we get. So BP is equal to, you just need to put in the values, and what you get is 1.366. This is 0.366, that is one. Okay, so this problem showed us the how to find the coordinates expressed in a rotated frame to that of the reference frame, and this matrix is called the rotation matrix. Now let's proceed further and see. We said the RZ theta was equal to cos theta minus sin theta cos theta 0 0 1 0 0. Okay, this is the rotation of Z by an angle theta. Now what about if you rotate about the x-axis by an angle, let's say if you about rotation of about the x-axis by an angle theta. Now what this will be? Now this is the rotation about x. So what we see is that the x component will become 1. So this will become cos theta minus sin theta, and sin theta cos theta, that is 1. Okay, and if I similarly rotate about y by an angle theta, then what will happen is the y component, so it will become 0 1 0 0 0. So this will become cos theta minus sin theta. This will become sin theta. This will become cos theta. So there are these 4 terms, cos, sin, which are moving around. And if you're rotating about z, then this one comes, this becomes z, z becomes 1. If you're rotating about x, x becomes 1. If you're rotating about y, y becomes 1. Okay. So this is very simple to understand, that this is called the rotation matrix. And the rotation matrix is with reference to which axis you're rotating about. Okay. So this is the rotation matrix. Now you can have more than one rotation. It is possible also to have more than one rotation at a time. Okay, so today we looked at the rotation matrix. So the rotation matrix gives us the relation of a point which is expressed in a rotated frame to that of the reference frame. Now you can have multiple rotations. So you can have one rotation about z-axis, then you can rotate about x-axis, then about y-axis, or in any order that you want. Okay. Now when you rotate about the x, y, or z, the rotation matrices are different, because if you're rotating about a particular axis, that particular axis component will become 1. Okay, so in the next class, we'll look at if you're rotating about multiple axes, what happens to the order of the matrices that you're multiplying. Okay, and then we'll move on to transformation translations. So we'll stop here today. Thank you.